Okay, so let's talk about Young's inequality, in this case for convolutions. So suppose that f in LP of, let's say, RD, and G is in LQ of RD, and that 1 over P plus 1 over Q equals 1 over R plus 1. Okay, so this is with 1 less or equal than P, Q, and R, and also less than infinity. Okay, then the norm of the convolution of f and g, norm R, is less than or equal than norm of f, and P, norm of g, Q. Okay, this is an important inequality. Okay, so some things to consider. If we take the Fourier transform that goes from L1 Rn to L infinity, one of the things that you can prove is that f is injective, okay, and the image of f, okay, this would be, let's say, L1 or Fn transform. Let's say that this is notation. Then one can prove that the image of f is included, not equal, but included to C infinity Rn. Remember that this is the space of continuous functions that vanish at infinity. Okay, we can also generalize a convolution theorem if f is in L1 Rn and G is in LP Rn and P between 1 and 2, then convolution of f and g transform psi f psi multiplied by psi. This is only a generalization. Now we're taking into account that g can be in p 1 or 2. Okay, and another important property, if f is in LP and g is in, let's say, LP prime, okay, then and with 1 over p plus 1 over p prime equal to 1 p infinity, okay, then the convolution of f and g is in C infinity Rn. Okay, continuous function vanishing in infinity. Okay, another property is. Okay, so now a theorem. Plancherel. Okay, so F is in L1 Rn intersection L2 of Rn. Okay, then F transform is in L2 of Rn, and the norm of F transform, norm 2, is equal to the norm of F2. Okay, so let's demonstrate this. Let's say that g of x is equal to f conjugate minus x. Okay, now using what we all the properties that we just said, now one can say that f convolution g is in L1 of Rn intersection C infinity of Rn. Okay. Okay, and the other thing that we can say is that the transform of the convolution is going to be equal to convolution of f and g. Okay, so we will have the g transform is equal to f transform conjugated. And so as we have this, then we will have that convolution of f and g is equal to the value of f squared. Okay, this should be transformed because, okay, this is because of the, because when one transforms a convolution, it is just the multiplication rule, and using this you obtain this. Okay, so knowing that, knowing this, now we can say that, and taking in consideration what we saw before, we can say that the convolution of f and g transform is in L1 Rn. And this is important because now, as we know that the transform of the convolution is in L1, we know that we can take the inverse Fourier transform and we will obtain the same formula. This is because this is positive, and there is also a property that if f is in L1 and f is continuous and point 0 and f is greater than 0, then f transform is in L1. Okay. So now, knowing all this, we'll write f convolution g on 0. Now, knowing the inverse theorem that we can apply, both functions convolutions are L1, then this is going to be integral in Rn f g psi d psi. There should be a parenthesis. Okay. So remember that we had that f convolution g transform is equal to f transform squared. So now if we consider the norm squared of f transform, now we will have this is equal to Rn f convolution g transform E C psi d psi, and this is equal to this, that these two things are equal, so this is equal to convolution of fg0, and at the same time this is equal to the integral Rn of fx g0 minus x dx, because that's the definition, and this will be equal to Rn fx f conjugate of x, because of how we define g, and this will be equal to f squared norm 2. So this is what we wanted to see. So this result shows that the Fourier transform is a linear bounded operator that goes from L1, Rn, L2, Rn into L2. It's an isometry. Okay? So this is going to extend our results to L2, which, as you may know, is a Hilbert space when you take in account a scalar product in L2. Okay, so one can prove that the Fourier transform defines a unitary operator in L2 of Rn. Okay,